All right, guys, so we are going to start learning about logs, not the logs you cut down from trees, but a function called logarithmic functions. Logs are actually the inverses of exponents. So these two questions here, 2 to the x equals 8, you might know that that's 3, right? 2 to the third power equals 8 because 2 times 2 times 2 is 8. But if I asked you, what does 2 to the x equals 6, what is the x value? Now you might not know. And there's no reason for you to really know because 2 to no whole number value is going to get you 6. However, you can have a decimal exponent or a fractional exponent. And we're going to learn to use these logs in order to help solve for these x's and to determine what are those values of those exponents that will help us simplify and solve these problems. Okay, so first off, what is a log? As I said, a log is going to undo an exponent. It's the inverse, kind of like adding and subtracting are inverses. Multiplication and division are inverses. Well, that's what a log is. A log is the inverse. It will undo the exponential functions and vice versa. An exponent will undo a log as we start getting into how to solve these. So basically, the base of your log is the base of the exponent, which should make sense, right? They're both bases. So a log base b of y, we call that the argument or the value here, is going to equal x, or the exponent. And I can go from logs to exponents and exponents to logs. I can rewrite them in any format. So in this case, just real quick, if I was to rewrite these, right, this is my base. These are all my bases. These are your values, and these are the exponents. And I can always test it out and see if it actually works, right? 2 to the 4th power does equal 16. 4 to the 0 power does equal 1. 12 to the 1st power is 12. And 1/4 to the -1, the base was a fraction. So that whole thing to the -1 is 4. Remember a negative exponent, I can just flip it. So that's how we would rewrite it from logs to exponents. And we can go vice versa. I can take an exponent, or I can give you an exponent, and I can rewrite it as a log if I want to. Again, things to make note is the base. That's the important part, right? Because whatever the base is of your exponent becomes the base of the log. So this is log base 5, log base 10, log base 8, and log base 6. The argument of your log, or the value of it that you're taking, is what your exponent equals. So log base 5, log 5 of the argument 25 equals 2. It's always going to equal your exponent. So log base 10 of 0.1 equals -1. You're just flipping places. Log base 8 of 4 is 2/3. And log base 6 of 1/216 equals -3. Now, please note when you write these out, you do have to write it as a little subscript. Don't write log big 5 and then 25. You want to write them as subscripts of the log. They're the base of the log as you go through these. Okay. All right, and we'll go through some more examples in class. Now, the next thing is we can evaluate them, and your calculator is going to do that work for you. We're going to use Desmos to do any evaluating if we need it. One thing to note, the common log is what we call base 10. Base 10 is the counting numbers that we're used to. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 numbers, so it's base 10. If I want you to do it in a different base, like base 2 or base 5 or base 12 or anything like that, that's when you'll need a subscript. But if there is no subscript there, if you just simply see the word log, it is understood to be log base 10. And that's going to come into play a lot more so as we start solving, and we need to know what the powers are going to be or what the exponent's base is going to be. So again, if it is not listed, if it just says the word log, it's not 0, it's not 1, it is 10. Okay, it's one of those times where it's not understood to be a 1. it is base 10 if there's nothing written. The other case is what we call a natural log. A natural log uses base e, the Euler number. Okay, that is going to be denoted by ln, lowercase l, lowercase n. It stands for the log of the natural number. So ln, logarithm of the natural number. So do not forget them. Please make sure you denote them correctly. So ln is the natural log. So whenever we have that, it is base e. And again, to evaluate these, we're going to use the graphing calculator in Desmos. We can't use the scientific one because for whatever reason, it will not do different bases in the scientific Desmos, but it will do it on the graphing. So if you go to the desmos.com/graphing and you type in log, you're going to hit shift minus. That'll bring you down into your subscript, and then you'll be able to type it in. And you'll notice that most of these are going to be decimal answers. So for the most part, we're probably going to be rounding to 4 decimal places, just like we were when we were simplifying our exponential functions previously. So just keep 4 in mind as we go through this. All right. This is where it's getting into play, where that we have to know their inverses. So as I've been saying over and over again, exponential functions are the inverses of logs and vice versa. They will undo each other. So you can see here that if I have log base b of b to the x, well, the base b of the log and the base b of the exponent cancel each other out. They go away. The word log even goes away because log is attached to its base. So the whole thing disappears and you are just left with whatever its exponent is. Same thing if I do the other way. If I have an exponent that the word log is in the exponent and the base of the log matches the base of the exponent, again, the whole thing disappears, it cancels out, and you're just left with whatever the argument is. So I gave you 2 examples to look at. I have log base 3 of 3 to the 4x. Well, a log base 3, the base of the log is 3, the base of the exponent is 3, they're dropping together. You are simply left with that 4x. So now I have 4x. And if I was getting into solving, which we'll get into a little bit later in the chapter, now I can solve for x. It's going to make my life easier to be able to get that x out of an exponential position so I can then solve for it. Now, the second one, they're different. I have a base of the log and the base of an exponent that are not the same, but I can get it to be the same. If I can rewrite the number in some format that can be written as a base that matches, then that's what I want to do. 9 I know is 3 squared. So if I have a log base 3 and I can rewrite its argument to be 3 to some power, I want to do that. So it's going to cancel out. So 9 I'm rewriting as 3 squared. Now I got log base 3 and the 3 of the exponential part, they're going away. They're canceling. So I'm left with the square and I'm left with the x that was originally there. So together they make the 2x. Okay, so again, that's very important. If you can rewrite it to have the same base, if you can rewrite it as an exponential value, do so. Get it to cancel out so that way you can use it to solve or do whatever it is that needs to be done with that expression. And again, we'll go through all of these. One thing to note, again, down here in 16, I have e to the ln. Base e is your natural number. Ln is your natural log. Those two are going to cancel. So this e and this ln are going to go away. You're going to be left with just the argument, which is 20. Okay. So again, be aware of the base logs of the natural base, e and ln, and of your common log, which is a base 10. And yeah, we'll go over these more in class. Okay. The other thing, since they're inverses of each other, I can find inverse functions. Remember, to find an inverse function, you swap your x and y, and you've got to get the y by itself again. So if we take a look at these 2 problems, I just rewrote f of x and h of x as y. I swapped their positions. So now I have x equals 3 to the y plus 1. Well, if I have to solve for y, I got to get the y out of the exponent position. So I'm still going to get it alone, move the 1 over. But now to drop down that y, I got to get rid of the 3. I got to get rid of the base that it's attached to. So in order to do that, I can do the log of both sides. I can do log base 3 of the left side and the right side. And log base 3 of this side over here is just log base 3 of, and then you put it in parentheses, the argument, x minus 1. On the left-hand side, well, log base 3 of a base 3 exponent, they're going away. I can cross those out. And now this y gets to drop down to be its function. Okay, so this is where knowing their inverses is going to come in crucially. Now, in the other one, this is if I have a log and I got to get this x out of the argument. Well, I can't move the 3 over because it's part of the argument. It's in those groupings. So I got to get rid of the log first. So after I swap the letters, again, I notice I have log base 5. In order to get rid of the log part, I got to raise it as an exponent. So you can see I have written 5 and the caret. So that is making it known to me that I am having 5 as the base, and then the left and the right side now becomes its exponents. So you can see on the right side, on the left side, the 5 raised to x is 5 to the x power. And the 5 raised to this log, well, they're going away. They're disappearing. And I'm just left with that y minus 3 now. Now the argument drops out, and I can move the 3 over and get the y by itself. Okay, so again, being able to utilize the inverses of each other to get the letter that I need to solve for by itself. Okay, and again, we're going to go through utilizing that. And the reason being able to do so, like I said, is more for solving, but we can even use it for graphing. So if I don't have a graphing calculator available, I can find a log to make it, or I can find the inverse of a log to make it an exponent, which will make it easier for me to find the values, right? Because I can figure out what 3 to the negative 2 is, and negative 1 and 0, 1 and 2. Those aren't hard for me to do in my head. So if this was non-calculator, I could do this. I could rewrite, get the inverse, make it an exponent, and then I flip it. Remember, inverses are swapping. We're flipping. So I flip this. You can even see my table completely flipped right here. And that then gets me this new log function, which is the inverse of the exponential one, which I have graphed up here. Now, because things flip and they're inverses, the domain and range also flips. Be aware of that. So if the domain in an exponential function is all real numbers, and if I change positions, now the range is all real numbers because domain was x. And if I flip it, now I've got to go to y. So you can notice I went from all real numbers in the domain to all real numbers in the range. And my range from the exponential functions, which we've practiced before earlier in the chapter, is y is greater than 0. And when I flip it, now it's x is greater than 0. When you swap those letters to make your inverses, their graphing are going to swap and their domains and ranges are going to swap. Okay. Now, again, most of the time we're not going to do this. We're going to have access to our calculator. We're going to have Desmos to help us out. Okay. So with Desmos, you can't use negatives. Negatives and zeros are undefined in logs. You do want to have a couple of fractional or decimal smaller values, because otherwise if you start at 1, you've just lost a good chunk of your graph. So I would highly suggest making a graph kind of similar from a quarter all the way to 4. So you have 0.25, 0.5, 0.75. Those will give you your good decimal values. And then you can do a couple whole numbers. You don't have to do too many, but just enough that you can get an idea of what the graph looks like. And then from here you can see now I have this curve happening. Okay. Again, the domain of all logs are going to be based off of your inverse of your exponents. So the domain in this case is x is greater than 0. And I can see in my table as 0 is undefined. So it can't equal 0. It has to be everything bigger than 0. I'm not going to have a negative on my x value. And then lastly, your range can be all real numbers. I can end up with any number in the negatives of the y's all the way to the positive of the y's in a log function. Okay, so again, we'll be going through all of this in class together. We're going to use Desmos a lot, the Desmos graphing calculator, to help us with simplifying and graphing.